Hello Cave Dwellers, thank you for joining us for part 2 of this lecture by Professor Steve Furber. If you haven't already seen part 1, then click on the link at the top of the screen now or in the video description. These talks and our museum are made possible thanks to the support of you, the viewer, our wonderful patrons and our sponsor PCBWay.com. So we thank PCBWay for their support and we recommend you check them out for their PCB design and manufacturing services, 3D printing, injection moulding and CNCing. And of course check out their shared projects where you'll find accessories for computers, including those created by Professor Furber. Go and visit PCBWay.com, but not before you've seen the concluding part now of Professor Furber's talk.
So building brains, this is a little bit about my research at Manchester. Which was focused on building computers for brain research from the outset. And of course, I'm not the first person to be interested in brains. Ada Lovelace, I've heard her name mentioned today once or twice. Generally, people in computing know she worked with Charles Babbage. Is considered by some to be the first programmer because she thought about algorithms that might run on Babbage's machine. And she wrote copious notes. Mainly about that side, Babbage and computing, but she also wrote notes about her thoughts on the brain, and this is one of them, where she says, I have my hopes of one day getting cerebral phenomena such that I can put them into mathematical equations. I hope to bequeath to the generations a calculus of the nervous system. Now, that was pretty high ambition. In fact, it's sufficiently high that even today, if I wrote words like that on a research proposal, it would instantly be rejected for being hopelessly overambitious. We're still nowhere near having a calculus of the nervous system. But Ada expressed strong interest in that direction. All credit to her. Coming a bit closer to home, or to today, in his last few years, Alan Turing lived in Manchester, actually quite close to where I lived until a couple of years ago when I moved to the East Midlands to be near my grandchildren. But when I was working at Manchester, I lived in Wilmslow, which is near the airport south of the city. And the other side of Wilmslow is this fairly indistinct semi-detached house where Turing lived. And it has a blue plaque over the arch, talking about him as a founder of computer science and about his cryptography work. While he was in Manchester, Turing wrote a seminal paper with the title Computing Machinery and Intelligence. And this paper begins with the words, I propose to consider the question, can machines think? And this is one of the earliest papers on the prospects of AI. It's worth remembering that this was written in 1950. Turing had moved to Manchester because the Manchester baby machine developed by Williams and Kilburn was the first in the world to implement Turing's big idea from the 1930s of the universal computing machine. And Turing was already beginning to think about where this technology might go. And in this paper, he says, well, can machines think isn't a very good research question. And he turned it round into what he called the imitation game, and what we simply know as the Turing test for human-like artificial intelligence. Now, in this paper, Turing reckons all a machine would need compared with the Manchester baby machine was more memory. And just to remind you, the Manchester baby machine had 32-bit words of memory, 128 bytes of memory, okay? Not gigabytes or megabytes, just bytes on a single CRT screen. And Turing reckons in this paper that it would need about a gigabyte. And he reckoned by the turn of the century, machines might have that much memory, and that was quite a remarkable prediction because it would be about that time that a PC would have around a gigabyte of memory. It would also be about 1 million times more powerful as a computer than the Manchester baby machine, but it would not pass his test, okay? And, well, I guess today you might argue that some of the large language models come close if they don't actually pass the Turing test, but they probably do, but then there's a debate as to whether it's the right test, but it's survived a remarkably long time as a kind of objective, even if it has now been passed, even though the machines that pass it don't think, right? My take as to why human-like artificial intelligence has proved so much harder than Turing and many people since Turing anticipated is because artificial intelligence is trying to mimic natural intelligence. Natural intelligence is based in the brain, and we don't understand how the brain works. Okay? So we don't really quite know what it is we're trying to build with AGI systems. And so that's kind of led me to think about, for the last 25 years, how we can bring computer technology to bear on improving our understanding of the brain. And the research was motivated by two sort of fundamental questions. We've now got formidable computing resources. Can we use those to accelerate our understanding of the brain? And as we know more about the brain, can we use that knowledge to work out how to build better computers? And so what is it we're trying to do here? Well, a few bits of biology. Your brain and mine largely comprises neurons and some other important cell types, but mainly brain scientists focus on neurons. And neurons are cells with multiple inputs through their dendritic structures and basically a single output. So when the inputs to a neuron match some kind of pattern the neuron's interested in, it produces an output, and its output is what's called a spike. It's a pure impulse. It just goes ping. So all your thoughts while you're sitting thinking about what you're going to have for dinner are patterns of pings flowing around between the neurons in your brain, to the best of our knowledge. Okay. And these neurons fire at a few hertz up to a few hundred hertz. And just as each neuron has many inputs, it also has many output connections. Standard logic designers' model of the world is the average fan in of a logic gate equals the average fan out, because you're just counting the same thing from a different end. So if you're trying to understand the brain, what you're trying to do is put enough of these together to get something a bit brain-like. And we each have, I think, there are about 86 billion of these cells in our heads. Other animals have smaller numbers. Or I think there may be some with bigger numbers too, but that's a different question. What fascinates me is that it's like a logic gate. It's a very flexible component. You can build a simple state machine with a handful of logic gates, or you can build a supercomputer with a few billion. Likewise, with neurons, you can build very simple animals with a few. C. elegans has 302 neurons. Honeybee has just under 1 million. We have just under 10 to the 11. Okay. And in principle, the more you have, the more you can do with them, although it's not clear that this is a linear relationship or anything. And what do we know about the structure of the brain? Well, neuroscientists have been digging into brains for a long time and know quite a lot about what's there. They can describe the structure of your cortex, which is the outer layer of your brain, which is a kind of flat sheet that's sort of crumpled up to fit inside your skull. And that has quite a regular structure. And the thing that sort of fascinates me is that that structure is very similar at the back of the brain, where it's doing things we can model and understand to do with low-level image processing, finding edges and corners and things. And the same structure applies at the front of the brain, doing things we haven't a clue about, such as natural language processing. But these things run on this very similar hardware, okay? The hardware is the same, and there's no software. So it suggests very strongly that the algorithms happening here and the algorithms happening here must be similar, but we don't know where that thinking leads. Now, there isn't enough information in your genes to define every connection in your brain. So the standard model is that your genes sort of say to this bunch of neurons, well, grow projections over there. You'll find some other neurons over there, connect to about 10% of them, okay? But the connection's made at random. And that's why human brains are so diverse in their neural capability. It's not fixed when the brain develops. As you use your brain, the brain decides some connections are not useful and drops them and looks for new ones. So your brain is constantly searching for more effective connections throughout your life. But that's how it gets its structures together, to the best of our knowledge. Remember, we don't fully understand the brain, so everything I say can be taken with at least one pinch of salt. And I'm not a neuroscientist, so I'm merely reflecting what I understand. When we try and model these, this has been done for a long time, since at least the 1950s. People sort of abstract the neuron into a simpler structure and then try and put them together to do something useful. And the explosion in AI we've seen over the last 20 years is the sort of current state of development of this. But it's built on stuff that happened well before. Certainly the principles of modern AI were developed in the 1980s, and some of the foundations of those principles go back to the 50s. Now, my general view of computing is if you want to build a good computer, you have to find the right balance between three fundamental processes. One is processing information, transforming it. One is communication, which is sending it around to different places. And one is storing it, remembering stuff. And storage you can think of as communication through time, if you like, but it's rather a different process. And the standard processing model is that a neuron computes a weighted sum of its inputs, passes that weighted sum through some nonlinear process, and then generates an output. And standard neural models as used in today's AI, those are inputs, and the outputs are sort of continuous variables. So they don't use the kind of spiking that you see in biology. They produce outputs which are usually thought of as representing the mean spiking rate of the neuron. And these things learn by adjusting the weights, and there are algorithms that have been around since the 80s which tell you how to adjust the weights in some optimal way. And that's what's going on when you train AI models. And the processing, well, this is, people who don't like equations needn't worry, I'm not going to go too deeply into this, but one of the standard models we use for the more biological neurons are called leaky, integrate, and fire. And these are the kind of things we model on the Manchester SpiNNaker system, where we think of the inputs as a time series of spikes. We still do the weighted sum, we feed it into a neuron. When the neuron gets sufficiently pumped up, it fires and emits its own spike. And that's okay. But there are all sorts of details. So biological neurons display habituation, which it means if you give them the same inputs all the time, they get bored. And so initially they spike in an excited way and then they slow down. And they have other characteristics that make them more complex. Communication in biological neurons is principally through sending these spikes around. There are other things going on. Neuromodulators are slower, more global processes. But spikes are the key, and they're asynchronous. There's no clock in the brain. There are rhythms, but no clock. And a spike is a kind of unit impulse. So the information is not in the size or shape of the spike. It's in which neuron fires and when it fires. So that's quite a nice abstraction for computing purposes, and leads to a technique called address event representation, where you basically give each neuron a number, and then you have a time series of numbers, each number representing the time when that neuron spiked. And it can spike many times, but then you can basically represent all the activity by a big time series of numbers. Now, so that's processing and communication. Storage. This is much more complex and much less well understood in the brain. The connection weights are the standard model of storage. Different stabilities. But also, if you think the information flowing down an axon takes about 20 milliseconds to get from one side of your head to the other, and we know we can build computers using delay lines of storage. I mean, things like EDSAC work that way. So maybe that's happening. Neurons interact in dynamic states. They grow new connections. New neurons appear in some parts of the brain. So we don't really know. So, you know, when you say you can remember what your grandma looks like, we've no idea how that's represented in the brain. You may be even able to draw a nice picture of your grandma if you're an artist. But again, we don't know how that information is stored. But it's some sort of combination of these things and maybe some others. So how do we model it? Well, about 20 odd years ago, we decided we'd use our computer engineering skills to build a computer to try and capture some of this and model it so that we could experiment with mechanisms. And we set ourselves the goal of putting 1 million of these ARM processors into one computer. From the outset, it was clear that even with 1 million processors, you only approach 1% of the scale of the human brain. Or as I prefer to think of it, 10 whole mouse brains. Now, what we know now, the mouse brain is very similar to the human brain, but 1,000 times smaller, so it's quite a convenient stepping stone. What we now know, even this looks a bit optimistic, because the models we're using 20 years later have got a bit more computationally complex and sophisticated. But I think we could probably do a decent job of one mouse brain, if anybody could tell us what the model was, which they can't. And to build the machine, we have to adopt some principles. This is getting a bit computer sciencey. So the first thing is, in the brain, I've talked about the cortex structure, but different brain regions have quite different connectivity patterns. And you don't want to rewire your machine for each different brain region. So we do the standard computer science thing of virtualizing the topology. So the topology you want in your model and the topology of the wiring in the machine are decoupled in a flexible way. We wanted to run at about biological real time, so we can build a machine where we don't have to timestamp things, time just models itself, so things happen when they happen. And we try and keep everything running at biological time. And the sort of fundamental computing principle is worry about energy, not about processors. Processors are free. The real cost of computation is energy. So with 1 million processors, you've almost certainly got more than you need. If you need more, you have more. And after 5 years of thinking, we came up with an architecture which is very simple. Like all the best ideas, we came up with this idea of just having a large two-dimensional array of nodes where each node contains a computing layer, which is the SpiNNaker chip we designed at Manchester, and a memory, which is a standard industry DRAM chip. And then we connect these through a 2D mesh. And unlike supercomputers, which often have sort of 5 or 6D toroidal meshes, we did the numbers, and 2D was enough for this problem, and it's much easier to build, much cheaper to build. So we then spent 5 years designing the chip, square centimeter with 100 million transistors on it. You remember ARM1 had 25,000. Here we have 100 million. That's not a big number. I'll show you some big numbers later. And we put them, in this picture, the SpiNNaker chip is the sort of lighter colored square, and the DRAM is the darker memory, which is literally glued on top and then gold wire bonded to make the connection. So the entire node is within this 2 centimeter square package, which you can then tile the world with. If you look at what's on the chip, it's just got 18 copies of processor with memory, which is this bit here. So all the frequently used memory is within a fraction of a millimeter of the processor. My simple model of energy required for a computation is it's the number of bits you need to move multiplied by the distance you have to move them. So keeping the distance small is fundamental to energy efficiency. The less frequently used stuff is on that DRAM accessible through that port that's about 1 centimetre away. And then the key to the machine is how we connect all this stuff up, which is this router in the middle. And this is basically a scaled down Ethernet router in many ways. So it's like the thing that sits in the corner of, in the rack in the corner of your office with all the Ethernet connections going in. But here it's occupying a couple of millimetres square in the middle of the chip. So it's cost reduced. And you can take that chip, you can populate a circuit board. The standard SpiNNaker board has 48 of those on. They look like they're in a square, except you'll see the top right-hand corner is missing. And that's because they're not actually a square, they're a hexagon. It's been morphed a bit. And so there are 48 chips. And if you start growing hexagonal arrays with 3 in the middle, then put a layer around and keep putting a layer around, you find 48 is one of the magic numbers that arises. I'll leave that as an exercise for the reader. And then those boards can be put in a big machine. And we had the sort of 500,000 core machine from 2016, and then the full 1,000,000 core from 2018, and that machine's been sitting in Manchester running an open service under the auspices of the EU Human Brain Project. So 24 hours a day. Unfortunately, it's proved very reliable in that, if you remember 2020, we had this COVID thing and the big lockdown, and for 6 months nobody could get near the machine, and it just kept working. So the service ran uninterrupted through the pandemic. Wiring the boards up is interesting. One of our students wrote a very nice little program to optimize the wiring. This is the 500,000 core machine, but the principles are the same for the full machine. So there are all the chips in their 2D array, mapped onto circuit boards, 600 in the case of 500,000 cores. All the people in my group work very fast. And then you've got to wire these together without any very long wires, because long wires are unreliable. And so the boards are basically interleaved. You avoid the long cables that you can see in that picture by doing this. And then you do it in the other dimension as well. And then the longest wire connecting 2 boards in the machine is just under 1 meter long. And even though the machine is in 10 sort of data center scale racks, we avoid long wiring. And the cables are installed by these guys, still working very fast. And if you look, they've got headphones on. This is not because they're listening to music. It's because they're each wired into a laptop, which is giving them written instructions as to where to plug the next end of the wire in. And they plug it in with the machine live, and the machine checks the wire when they plugged it in. So mistakes are not made because they're all checked. The guy who wrote the program was the one standing at the end, Johnny Heathcote, who now works for the BBC somewhere. So there they all are, wiring 600 boards together with 1,800 wires. And it took them 4.5 hours to do the whole machine, which was without any mistakes, as I said, because Johnny's software was totally reliable. How does the machine operate? Well, there's basically one simple principle. The brain's very highly connected, and it's matching that degree of connectivity that was the challenge in the architecture of the machine. And we use address event representation, so when a neuron spikes, the processor modeling the neuron drops a packet into the fabric, which says neuron number 25 just spiked. And then the fabric is responsible for delivering that packet everywhere it's needed. So it has routing tables, and the packet comes in and the key says it's 25. You look it up, decide where it has to go, and then it can go to any or all of the local processors and any or all of the adjacent chips. And so effectively you can build an arbitrary tree across the machine. The packet will flow down to get to 1,000 destinations, all within a small fraction of a millisecond. So that's how that works. We don't expect our users to understand the machine in detail. So they program it in a high-level language called PINE, which simply stands for Python Neural Networks, and is used by a number of machines. And then the software stack, which took longer to build than the machine, maps those problems onto the machine and generates the results. And we've been making the machines for quite a long time now, so there's about 100 of them distributed through labs around the world. That was a snapshot at one particular time. So, and what does it do? Well, it was designed for brain modeling. So an example I've talked a bit about is the cortex. We had a kind of informal competition between the SpiNNaker team and a team in Jülich running a supercomputer and a team in Sussex using GPUs. And we were all trying to run exactly the same model, which was a Jülich model. And SpiNNaker was actually the first machine to achieve biological real time with this model. The others all got there in the end, and we all learned quite a lot off each other. So it was a very constructive competition.
Surprising thing that it's done so far?
Sorry?
What's been the most surprising thing that SpiNNaker's done so far?
Worked. No, I mean, getting first real-time version of the cortical model was one of the pinnacles of what it's done. The cortical circuit is quite easy to draw in slightly simplified form. It's very different from an AI network in that, here you see inputs going in at different places, outputs going out at different places, and everywhere information's flowing back and forth. And we don't understand this, okay? We can draw it, it's quite simple, it's well understood structure, but what it does is not understood. It's one of the challenges. But what was particularly impressive is, with being the first to real time, is of course we're using 20-year-older technology than all the HPCs and GPUs. So one of the big philosophical debates in this space is, is the brain just a bunch of neurons, a big bunch of neurons, wired together in a particular way, which when you switch it on, thought and consciousness emerges. It's consciousness and immersion property of your neural network. Or is there something else going on? And so one of the questions is, if I build an equivalent network on a machine like SpiNNaker, and it's got the same structure and the same complexity, which we can't yet achieve for scaling reasons, but if we could, would it then become conscious? Or would it not? Would it think? Would it not? And we don't know. I mean, if you read around this area, there's literature on all sides here. I mean, one of the better known ones is a book by Roger Penrose.
Microtubules.
Sorry?
Microtubules, isn't it?
Yeah, I mean, the book's called The Emperor's New Mind. And it's basically claiming that, the whole of AI is an illusion. And that, nothing that's Turing computable can possibly replicate the human brain, right? And he says there must be other things going on. He doesn't say definitely what it is, but he says it might be, for example, quantum effects in the microtubules in the neurons. Now, most neuroscientists I talk to think he's wrong. And the book, of course, I mean, Penrose is a mathematician, so the book presents a very mathematical argument as to why this has to be the case, but it's fairly easy to spot flaws in the argument. But it's an area for debate, so we don't know. But we might find out. Just to finish this bit, because I realise I've kept you probably as long as you were expecting to be stuck here, but also within the Human Brain Project, we developed a second generation chip with collaborators at TU Dresden, and SpiNNaker 2 has existed for a couple of years and is now appearing in large scale machines that are being actively sold by SpinCloud Systems. You see they've gone for a nice sexy curved arrangement of the racks as opposed to our boring straight line. But I mean, this is the machine they built at TU Dresden, and it's about 5 million ARM cores. in the machine. So it is now being commercialized, and interestingly, their target market is not brain science, because the world has moved on. Their target market is running large AI models at much lower energy than big, NVIDIA GPU systems. And if they can demonstrate that convincingly, then there'll be a big market, because everybody's very worried about the unsustainable energy demands of big AI. And I think there's a potential with this kind of technology to reduce those energy requirements by 2, possibly 3 orders of magnitude. Because the problem with, I don't think I've put this argument in here, the problem with standard GPU AI is it computes everything all the time. And we know, and everything's connected to everything, the connectivity is dense. So the brain's never densely connected. And we know that 98% of the parameters in big AI models do nothing. Right, so we can get rid of 98% of the parameters. Then the GPU is a terrible way of computing sparse matrices. So you need something that's good at sparse matrices, which these are, because that's intrinsic to biological modeling. And we know in biology that only a few % of neurons are active at any one time. So you reduce the activity, and again, these machines can do this. So you've got about 2 orders of magnitude of spatial sparsity and about 1 order of magnitude temporal sparsity. And if you can get all that to come together, which is not a trivial undertaking, but if you can, that's a factor 1,000 reduction in energy, which will be a big deal if it's done. So that's what I wanted to say on SpiNNaker. I mean, there's a lot, you're not my normal academic audience, so that's fairly curtailed, but well, let's leave it at that for now. What I wanted to finish on was just this 40 years of Moore's law, because this again roughly corresponds to my career, okay? I've been designing computers of various sorts, well, since the late 70s, so it was a bit more than 40 years, but the comparison I wanted to just sort of highlight, because I think it illustrates what's been going on for these 40 years very well, is a comparison between the ARM1, which I've talked about, and the Apple Silicon M1, which was about 40 years later-ish. And this Mac, by the way, is an M1 Mac, so as soon as Apple announced a computer that was ARM-powered, I had to buy one. So, so I did. And it's still, that's 5 years ago. Now, Moore's law, 1965, you need to be very precise about this, was about the number of transistors on a chip. And he predicted the number on a chip would double every 18 months to 2 years. Let's take 2 years as the slowest. And in 65, he reckoned that will continue for 10 years. And it's actually continued. So now you've got a factor of 1 million in terms of transistor count. Right? And all the other things that come with Moore's law are kind of side effects, such as higher performance, better energy efficiency, and so on. They're all a result of the fact that the way you deliver Moore's law is by making the transistors smaller. And smaller transistors are generally cheaper and faster and more energy efficient. Well, they were down to about 30 nanometers. Beyond 30 nanometers, it then becomes a bit questionable. But anyway, so how do the numbers stack up? ARM1 was a full chip, 25,000 transistors. M1 was a full chip, little bit bigger, but same order of size. Those pictures are roughly to scale. M1 is 16 billion transistors. Okay, that's a factor of 1 million. Okay, so Moore's law is real. You can debate how long it will continue forward, because physical limits are very much looming. But certainly for those 40 years I've been playing in this business, that all seems valid. How is that achieved? Well, making transistors smaller. So ARM1 used processes with a 3-micron feature size, which means that your wires and your transistors are a small multiple of 3 microns in dimension. And that's pretty small. But M1 is 5 nanometer. Okay, so that's roughly 1,000 times smaller process. Now, the interpretation of these numbers has got much looser with the sort of the nanometer scale stuff. What does 5 nanometer really mean? We can argue about. But we can see that, you know, if you make things 1,000 times smaller in linear dimension, that's 1,000,000 times denser in areal dimension. As I said, physics is beginning to bite. You do get about 4 silicon atoms to the nanometer. So a 5 nanometer feature is 20 atoms across. This is getting tricky. Throughout my career, the end of the world for Moore's law has always been about 10 years away. In the 90s, the end of the world was about 1 micron, because visible light, you know, the blue light with the short wavelength has a wavelength of about 300 nanometers. You can't possibly draw anything that's, you know, smaller than 3 wavelengths. Well, actually, it turns out you can. And we now routinely draw features which are a fraction of the wavelength of the light we draw them. Although for 5 nanometer, had to go to EUV, which is incredibly expensive. Because EUV light's about 30 nanometer wavelength, and nothing is transparent to EUV. So EUV has to be done in a vacuum. You can't make masks with, you know, glass with patterns on because the glass isn't transparent. So you have to make the masks on mirrors. So it's all done in a vacuum with mirrors. And of course, you've still got the issue that your mask is not the pattern you're putting on the chip. Your mask is a diffraction grating whose combined effect with other masks results in something close to the pattern you want on the chip. It's really scary. How are we doing? How does this map into performance? As I say, Moore's law is about a number of transistors, but it does affect performance. And if you look at ARM1, the first ARM chip ran at about 6 megahertz reliably. It was a 32-bit chip. M1 runs at 3.2 gigahertz, and it's 64-bit. So that gives you about a factor of 1,000. But of course, M1 isn't just a processor. It's got 8 ARM cores on there, and a whole lot of other stuff. But just looking at the standard CPUs, if you put all these things together, you're getting about 10,000 times the compute performance, ignoring, you know, the GPU that's on the chip and the neural processor and all the other stuff. So there's some of the other stuff, so you can see what else is happening. The DRAM is not actually on the same physical piece of silicon, it's on the same substrate. And there's lots of stuff going on in there. If you look at memory is also based on silicon. And the first usable ARM1 system shown on the left had 4 megabytes of memory distributed across 64 memory chips on that board. And the M1, you can have 8 or 16 gigabytes. This has 16, and they're in 2 packages, okay? And in fact, they're these 2 packages. I think if I do that, those are the memory chips. It's a picture of a black object against the black background. It's a very much Hitchhiker's Guide sort of photography. But you can see that, you know, the size of the memory is increased by a factor of 1,000, and the density of the memory is increased by something like 100,000. So it's not quite the million, but it's still very big numbers. So that's how Moore's law has worked out over my career, and I think it's quite interesting to see that, you know, it was a prediction made in '65 for 10 years, and it's actually worked for 55 years, but it's not going to work much longer. The only way we're going to deliver something close to Moore's law in the future, although people still claim smaller transistors, But basically the next big thing that's going to happen is going into the third dimension. And I've been working on some numbers recently as to what's possible there, and it's pretty impressive. I mean, the SpiNNaker chip, you know, these chips are made on silicon wafers that are 0.8 of a millimeter thick. But all the active stuff is on one side of the silicon. So to get the SpiNNaker chip into that package I showed you earlier, they grind away the back of the silicon until it's about 0.1 millimeters thick, right? And that's because the package can't take anything much thicker with 2 chips in. But if you look at the flash memory in your SD cards, or they're doing that all the time now. All those flash memories are multiple layers, and they're grinding them down to about 20 microns, I think, thickness, and then stacking them vertically. Now, if they start doing this with all the compute resources, then you can see, well, the numbers I worked out is you'd be able to produce an electronic equivalent of the mouse brain in about the same volume as the mouse brain, about a cubic centimetre. And well, that's kind of my prediction for where this might go in the next 40 years, but who knows. So I'll wrap up. It started with the ARM1 back in 1983 to 5, and then the Archimedes came out in 87. And that was ARM starting in a small way in Acorn's desktop products, which is what it was designed for. And now, you know, it's cropping up everywhere. It's finding its way into all sorts of machines. For a couple of years, the world's fastest supercomputer, the Japanese Fugaku machine, was ARM powered. I think that the top of the top 500 is now an NVIDIA machine. Again, that's got ARM processors in the GPUs, but the main compute is the GPU rather than the processor. And it's in my laptop, it's in watches, phones. One of the most scary things is I asked what's the technology in the AirPods, you know, things you stick in your ear. And I think they have quad-core 64-bit processors in now. In each ear. You hope they've got the power management under control for that. And with that, I will stop. If you, in the event you want to know more about SpiNNaker, we published an open access book, which means it's free to download. That's available from the publisher. If you feel rich, you can buy it on paper, but the PDF is free. And that covers the kind of first 20 years of the project. But with that, I'll stop, and I'm happy to take any further questions. How are we doing for time?
On behalf of everybody here at the Retro Collective, we hope you've enjoyed this 2-part lecture from Professor Steve Furber. A huge thank you to him for taking the time to visit us, to everyone who attended, and of course to you for watching. Please take the time to subscribe if you haven't already done so, and we'll see you in the next video.